Okay, we're recording. So, if we look at the first question on the lab sheet about cloud formation, when we filled our empty plastic bottle with a little warm water and we sealed the lid and we squeezed the bottle and we released the pressure, what did we observe? The very first time we did it.
Oh, nothing happened.
Nothing happened. So we didn't observe anything the first time we did that. So then the next step says open the bottle, drop in a lit match, not a lit match, must edit, drop in a light a match, blow it out and drop it in. Dropping in a lit match will usually melt the super thin plastic bottles and it's bad. But when you drop in a smoking match, it provides dust particles in the air. And then what did you observe? Brian, what did you observe after we had some smoke in the air? Do you observe anything with that kind of bottle? He's got a Gatorade bottle. Did it work? You made a cloud? All right, so you observed a cloud form. So even those thick-walled plastic bottles seem to work. That's good to know. So if you then squeeze the bottle again, what do you observe? Well, what?
No, we squeeze it and nothing happens. It's all clear.
Okay, so the cloud disappears when you re-squeeze the bottle. Joshua? They're all over, so just pass them down to him, like a handful. Okay, so here's some background information. Gases and liquids both have the property that they flow to fill the container that they're in, right? So if you have water in a tall, thin container, it will fill it and make itself into the shape of the container. If you have a long, wide container, the water will also, you pour it in, it will flow and fill the container that it's in. When you have a gas, the same thing happens. It fills the container it's in. The gas in this room doesn't just hang out here with us where we need it. It fills into every corner. It goes everywhere that it can get. Gases fill the container that they're in. The air in the bottle has less space, but there's still the same amount of air when you squeeze the bottle. It's compressed. The same amount of gas is taking up less space. When you release it, the air expands. No energy is added, but the expanding uses energy, so the air cools. And cool air can't hold as much humidity as warm air, so some of the water vapor in the cooler air condenses. So when the lid is on the bottle, can any air molecules get into or out of the bottle? No. Hopefully not. We're making that assumption anyway. We're assuming that no air molecules can get into the bottle and none can get out when the lid is on. Molecules are very small. Gas molecules, some gases have incredibly small molecules, but we're just assuming that no air is getting in, no air is getting out when the lid is on the bottle. So, is the temperature of the air in the bottle higher or lower when the bottle is compressed?
Higher.
Higher. The temperature is higher when you're squishing on the bottle. Then when you let it go, the temperature will go down. So what is the process by which air cools when it expands? Adiabatic cooling. So, like for example, I would say, oh, my coffee mug is old, it's getting lousy, it's no longer adiabatic. What I mean is, what is the goal of a coffee mug? Keep your drink hot, to not allow heat to escape from the mug, right? Or if I'm trying to keep my drink cold, to not allow heat to come from the outside into my drink, right? We want to prevent the movement of heat. So if I'm using an adiabatic container to hold my coffee, I'm saying that container is good at not allowing heat to get in or out. And so adiabatic cooling means no heat change, no energy change is happening. But there's a temperature change because if you think, there's the same number of air molecules in this bottle, assuming that the lid functions well and no molecules are getting in or out, right? So if a thermometer were in there and I squish in on it, then all those molecules have to fit in less space than they used to have. Would an air molecule be more or less likely to crash into the thermometer in less space? Max? It's more likely to crash into. So when they crash into the thermometer, that's what makes the temperature reading happen, right? Air molecules impart their energy to the thermometer when they crash into it. So when you have more likely collisions with air molecules in the thermometer, the temperature's higher. When I let go, and the cloud forms, can't see it anymore, then the gas has more space available, less likely to crash into the thermometer. The temperature is cooler. At a cooler temperature, then the air can't hold as much water vapor, so some will condense. So now you're going to have to write a little paragraph. Why did a cloud form when dust was present in the air, but not when there wasn't any dust? So I'm going to copy onto the board when somebody tells me what I should write. Maybe. I might write on the board in a minute. Ooh, yay. Okay. So think for a minute, consider what you want to write, and then we'll try to make one good paragraph out of what everyone writes. Do you have your sheet? See if I have one. Were you here last week? You weren't here last week, were you? Not ideal. That isn't good. I have this one for you, but I don't have. It's in the Dropbox, so the lab from this week. So maybe just take a piece of paper and write down answers, and then we'll just have to copy it onto it. Okay, so who wants to try? Why did a cloud form when dust was present in the air but not when there wasn't any dust? Okay, Jenna.
Because the water needed the nuclei, the cloud formation nuclei, to condense on, because without it, it'd have no place to condense.
And if you have something a little different, it's probably just fine.